Hello and welcome to our presentation of our final report about immersion lithography. My name is Lukas Jörg Schimmel and I'm an exchange student here at NTU. My partner is called Joseph Hanger and he will discuss with you the challenges of immersion lithography at the end of this presentation. So basically, we need to first clarify what exactly is lithography. Lithography is the process of transferring a geometric pattern from a mask onto a substrate. Most of the time it's a silicon wafer using light. Here on the image on the right you can see the light beam going through a mask and being focused by a lens onto a wafer. The three most important characteristics of a lithography machine are resolution, which is the minimum feature size you can achieve with this machine. Accuracy is also very important. It is how likely, the chance how likely it is that a machine produces an error-free chip. And productivity describes the throughput of the machine, so basically how much wafers can be manufactured and processed per time. One very important thing to consider for the feature size on a chip is the Rayleigh criterion. So basically you can see on the image on the right how a general lithography machine works. So we have a lens system, and from this lens system at the end we have a light source passing through a mask. The mask is the design we finally want to have on the chip. But the mask or the light gets diffracted at the openings of the little openings in the mask. So we have a first order maximum, second order maximum, or what we have learned in the lecture as well, we have iridescence. So we have a blurry spot in the middle and we have concentric circles around it, which are the maximums. The Rayleigh criterion says that two adjacent points can only be resolved if the main maximum of one diffraction disk falls into the first minimum of the other. The formula for the Rayleigh criterion is the critical dimension is defined by K1, which is a process factor, times the wavelength lambda of our light source, divided by the numerical aperture. You can further decrease or further reduce the critical dimension by lowering K1, but this has a theoretical limit of 0.25 as stated by ASML, and we are already really close to it, so we can't really further reduce the critical dimension with K1. Normally, before immersion lithography, we used lambda, so the wavelength, to decrease feature size. But we can also increase numerical aperture, and this is essentially what immersion lithography does. At that time, the industry standard for the light source was argon fluoride with a wavelength of 193 nanometers. The next possible wavelength is 157 nanometers, but the material used for that had some intrinsic unsolvable material science problems. So the basically lenses which were used absorbed this light at this wavelength, and we needed a new material for all the lenses, which is calcium fluoride. But this crystal is really difficult to grow, and the material properties are not favorable for lithography. That's why we need immersion lithography to increase the numerical aperture. So now we get down to the details of immersion lithography. Basically, after the last lens of our optical system and the lithography machine, normally we would have a gap between, a gap filled with air between the last lens and the wafer we want to manufacture. Now, in immersion lithography, we fill this gap with water. And water has a higher refractive index compared to air. So we increase N in the formula for numerical aperture, so we can increase numerical aperture. This allows for higher resolution while maintaining the industry standard light with a wavelength of 193 nanometers. Hence the name 193i of this technology. We use ultra pure water because it has some favorable material properties, and especially it's already available in every fab and conform with Morse lens coating. So this was really lucky. Here you can see a ray tracing diagram of a system, like again the last lens of the system and the silicon wafer and the gap. And you can see when the gap is filled with air that the angle of total reflection is larger, as you can also derive by Snell's law. Here you can see Snell's law, and if you increase the refractive index of the gap material, gap medium, then the angle of total reflection gets also increased. Also, because of water, the rays get less refracted, so we can move the lens further away from the wafer, so the focal point is still at the level of the silicon wafer. The immersion effect is basically to increase the numerical aperture to higher than the number of 1. So the theoretical limit for the numerical aperture with air is 1, because basically if you just set alpha to 90 degrees. But if we want to have a higher numerical aperture, we need a new material or new medium, which is water in this case, with 1.44 refractive index. So we can achieve a higher NA than 1 with water. But a difficulty, or a challenge, is that the depth of focus gets decreased with a higher numerical aperture, but it's still manageable because we have precise wafer stages and planarization techniques. On this table, you can see different lithography, different technologies for lithography. Water handling is very important because it sounds paradox to use water in such a sensitive machine, but there are design considerations which need to be where you need to be aware of. We need constant supply of fresh, temperature-controlled, ultra-pure water. The water must be held exactly under the lens, and the speed of filling and emptying the gap is crucial for throughput. We decided for a shower head, or the industry decided for a shower head configuration, which means you pump in water and suck it out with a vacuum, and the water is only on top of the wafer, and the wafer is not like surrounded by water, because that brings other challenges.
I'm going to go over some challenges with immersion lithography. Immersion lithography is prone to many defects such as bubbles, watermarks, and particles. During the process, water between the lens and substrate can contain bubbles that stick to the resist surface. This can cause light to refract, which displaces the light intensity, causing circular distortion. This can be generated by outgassing from the resist, turbulent flow, or other contaminants. To reduce bubble formation, headings are designed to remove gas from immersion water and the use of low gassing resists. Also, droplets left over on a wafer surface after exposure and drying causes watermarks. When the droplet evaporates, it leaves behind a residue, which this residue can block the etching process. Ways we are working to reduce watermarks is to use hydrophobic top coats, highly purified water, and to make sure to properly rinse and dry the wafers. Particle defects in immersion lithography are challenging because water is effective at transporting contaminants and debris. This is one of the main leading causes of loss of yield. Also, because immersion lithography has a higher numerical aperture, the critical size for a particle to interfere is much smaller, between 15 to 25 nanometers. The process of using water to increase numerical aperture for imaging was first used in high-resolution microscopes. The idea was first proposed by Rebbe Hooke in 1979 in his presentation, Lectures and Collections. The first implementation of an immersion lens was by Professor Amici and Mael. They used oil instead of water between a lens and glass sample. And it was not for the purpose of increasing numerical aperture, but to reduce aberrations. But in the context of lithography, the first person to propose the idea was Bern Zhenglin, who was a Taiwanese engineer working at IBM in the 1980s, and founded Innovation Incorporated. ASML is currently the industry leader in almost all and almost all chip manufacturing companies use immersion lithography, such as TSMC, Samsung, and Intel. This is one of the main products produced by ASML. There are two categories of multi-patterning, one being pitch splitting and another one being adding spacers. Pitch splitting, there are two techniques called double patterning and triple patterning. Spacers have self-aligned double patterning and self-aligned quadruple patterning. In double patterning, the etches get split into two processes, which are superimposed later, effectively doubling the revolution. And self-aligned double patterning is mostly used in flash memory because of its simple pattern. In computational lithography, as etching becomes smaller, the deformations from the mask to the substrate become more severe. Many causes of this are diffraction, interference, and imperfect chemical reactions. Computational lithography is a method of calculating a mask to counteract the predicted deformities. Algorithms are being developed using trial and error. AI is also being used heavily in research for creating effective and efficient masks. Extreme ultraviolet lithography uses wavelengths of 13.5 nanometers and can allow for resolutions close to 13 nanometers. It's a very complicated process, but the basics is 10 droplets are hit by a high-power laser twice. The first flattens the 10 droplets, and the second vaporizes them into a plasma that emits 13.5 nanometer light. The light is reflected and focused into a series of ultra-smooth, multi-layer mirrors. Thank you for watching our presentation.